All right, everybody, I hope you are having a great day. In today's lecture, we are going to be talking about isotopes and atomic mass. So in our last lecture, we introduced the concepts of the structure of the atom in terms of where are the proton and the neutrons located, spoiler alert, in the nuclei, versus where the electrons are in the electron cloud around the nuclei. And we spent some time talking about how we can change the number of electrons in order to make different ions. And we also talked about how you can't change the number of protons, right? So protons are the constant. They cannot change because they are the identity of the element. However, one thing we can change is the neutrons. So we, again, just as a reminder, we can change our electrons, we can change our neutrons, but we cannot change our protons. So when we have molecules that have a different number of neutrons, but still the same number of protons, we have what is called an isotope. So again, isotopes are atoms of the same element. Because they have a different number of neutrons and because neutrons have mass, then isotopes will have a different mass number. By definition, isotopes have the same number of protons but different number of neutrons. And they can be distinguished by their atomic symbol. So often when we write atomic symbols, we will indicate what the element is, what the mass number is. Remember, the mass is the sum of the protons and the neutrons, and the atomic number, which reflects how many protons are there. Now, one thing you may have noticed is in the periodic table, we're not seeing whole numbers here, right? So for magnesium, the periodic table reports the atomic mass is 24.31. And you might have been asking yourself, why is it not a whole number? If protons weigh 1 and neutrons weigh 1, why is this not just 24 to represent 24 protons and 24 neutrons? Where is this 0.3 coming from? Well, what we're reporting in the periodic table is actually something called the average atomic mass of what we are seeing as naturally occurring isotopes. So magnesium is an element that has 3 naturally occurring isotopes, and we can see that that is magnesium 24 to show that we have 12 neutrons, magnesium 25 that has 13 neutrons, and magnesium 26 that has 14 neutrons. Now, the overwhelming abundant isotope is that magnesium 24, where we have 12 and 12. We can see that there's about 78.7% of magnesium is magnesium 24, where about 10% is the isotope 25 and 11% is the isotope 26. So what that means is if I had like a bowl of magnesium in front of me and I reached my hand in and pulled out one of those magnesium atoms, 78% of the time it would be this isotope, magnesium 24. However, some of the time I might pull out magnesium 25 and sometimes I might pull out magnesium 26. If I do that 100 times, I'll probably find out that 78 times is magnesium 24, 10 times I'll pull out magnesium 25, and 10 times I'll pull out, or 11 times I'll pull out magnesium 26. So again, this is just sort of your natural abundance, or how often do these isotopes show up in nature. So again, if we look at the atomic makeup of each of these isotopes, we see our most abundant magnesium 24 has 12 protons. Again, our atomic number is 12. We know if it's a neutral ion, the electrons are equal, so 12. Because the mass number is 24 and we can subtract 12 from 24, that gives us our neutrons of 12. The atomic mass unit is going to be 23.99 or 24 essentially, because again, protons weigh 1.0007, neutrons weigh 1.0007. You add that up 24 times and you're going to end up with 23.99. And as I mentioned, about 78.7% of all the magnesium on the planet is this isotope, right? Magnesium 25, everything else is the same except we have one extra neutron, which is going to increase our mass by 1, and that is only about 10% of the time we see this isotope. And then magnesium 26, we have yet another neutron, which is going to increase our mass to 26, and this is going to occur about 11% of the time. Okay, so all over the world, we see that 78.7% of the magnesium is the 24 isotope, 10% of the magnesium in the world is the 25 isotope, and then 11% of the magnesium in the world is the 26 isotope. All right, so let's practice this with carbon. So naturally occurring carbon consists of 3 isotopes, carbon 12, carbon 13, and carbon 14. So in this question, we are going to state the number of protons, neutrons, and electrons in each of the 3 isotopes and assume all are neutral. So if we go back to our periodic table, let's go find one in this lecture. Here we go, right? We can see carbon right here. So carbon has the atomic number of 6. Therefore, we know that carbon must have 6 protons, and that is consistent for all 3 isotopes. Remember, we cannot change the identity of our isotopes. We can't change the number of protons in our atoms, right? Protons is the identity number. So I'm going to put 6 into each of these columns here for protons for all of our isotopes. Now, the question says assume all are neutral, so we are going to assume that we have the same number of electrons for protons in order for us to have a neutral charge. So that means the number of electrons for all 3 isotopes is also 6. So 6, 6, and 6. Okay? Now for neutrons, this is what we can change in order to get different isotopes. So if we have carbon 12, 12 is representing the atomic mass for that isotope. We know we have 6 protons. Therefore, 12 minus 6 is going to give us 6 neutrons. For isotope carbon 13, again, we still have 6 protons, so 13 minus 6 is going to give us 7. Finally, for carbon 14, again, we still have 6 protons. We cannot change our number of protons. Therefore, 14 minus 6 equals 8 neutrons. So in our isotopes, the only thing that is changing is our number of neutrons. For carbon 12, that is 6. Carbon 13, that is 7. Carbon 14, that is 8. So how do we calculate the atomic mass? So if we have all of these different isotopes. So what we are actually calculating is something called the average atomic mass. So the atomic mass that's reported in the periodic table is the weighted average of all naturally occurring isotopes of that element. This is the number that we see on the periodic table below the chemical symbol. So if we look at chloride, for example, chloride's atomic mass is 35.45. That is the average mass that represents the percent abundance of chloride 35 versus the percent abundance of chloride 37. So an average, a weighted average is just like when you're calculating your grade for a class, right? You have homeworks, that's so many points. You have exams, that's so many points. You have labs that are so many points. And then each of those categories has a weighted average. So maybe your exams are 50% of your grade, where homeworks are only 10% of your grade, right? So they all have points, but then once they go into the average of your grade, they may have different weights or different effects on that points, on that grade. And so that's what we see when we look at the average atomic mass. So to calculate that, you will use the experimentally determined percent abundance of each isotope of that element and then multiply that percent abundance by the atomic mass of that isotope. Then you sum it all together. So let's take a look at chloride as an example. So chloride has two isotopes. We have chloride 35 and chloride, that should be 37. It's a typo right there. The average atomic mass of chloride 35 is 34.97. For chloride 37, it's 36.97. So we take their masses and then multiply them by their relative percent abundance. So if we go back, we see that chloride 35 is 75.76, where chloride 37 is 24.24. So again, we plug that percent abundance into our calculation for each isotope, multiply 34.97 times 75.76 divided by 100 equals 26.49 AMU. We take our other isotope, the 37 isotope, multiply it by its percent abundance, and we get 8.962. Then we add these two numbers together to get our average atomic mass of 35.45. Again, this is what we see calculated in our periodic table as the average atomic mass for chloride. So let's practice this again with lithium. So lithium consists of two naturally occurring isotopes, lithium-6 and lithium-7. If the average atomic mass is 69.41, which isotope do you believe is the most abundant? So here we're not even going to have to calculate. I just want you to think about it, right? So if the average atomic mass is almost 7, which are we leaning closer towards? Are we leaning closer towards lithium-6 that has a mass of 6? Are we leaning towards lithium-7 that has a mass of 7? Well, if you answered lithium-7, you would be correct, right? We can see that this number definitely is closer to the atomic mass of 7, meaning this isotope is our most abundant. Now, because we are not 6.99, we're 6.941, that tells us that there is a little bit of lithium-6 there in the world, just not as much as 7. We might have a ratio of like 80% lithium-7 and 20% lithium-6 or something like that. So let's actually practice the calculation this time. So gallium is an element found in lasers used in CD players. I don't know if anybody actually uses these anymore. But in a sample of gallium, there is 60.10% gallium-69. Here's that average atomic mass, or that atomic mass units, and 39.9% gallium-71, which weighs 70.925 atomic mass units. So given this data, let's calculate the average atomic mass of gallium. So in this calculation, the first thing you want to do is analyze your problem. Remember that your givens in this type of calculation will be your percent abundance, so 60.10% for gallium-69 and 39.9% for gallium-71. And we also have the atomic mass for each isotope, right? So 68.936 and 70.925. We need, right, it's asking us to calculate the average atomic mass. So to do that, we are going to use that weighted average calculation. So in step 1, we have to multiply the mass of each isotope by its percent abundance divided by 100. So in order to do that, let's do for gallium-69 first. So the average atomic mass of gallium-69 is 68.936 times, open parentheses, 60.10 divided by 100, close parentheses, equals 41.43. So I'm going to write that down really quickly. 41.43. Now for our second isotope, gallium-71, the mass is 70.925 times, open parentheses, our natural abundance, which is 39.90, divided by 100, close parentheses, equals 28.299. I will then add the two numbers together, so 28.299 plus 41.43, oops, 0.43, and that is going to give us 69.73. Let's take a quick look at sig figs. Our experimental number is the percent that it was found experimentally, and that is 4 sig figs each. So yes, I should report 4 sig figs. So 69.73 AMU is our average atomic mass. Again, we notice that the majority is the gallium with 60%, so our average is going to lean a little closer to gallium 69 than it is gallium 71, but we have a significant portion of gallium 71, 40%. So that's why we're going to be a little closer to 70, somewhere in the middle between 69 and 71. All right, so now it's your turn to practice. So I want you to log into our Pearson system, Mastering Chemistry. The password for this assignment is Isotope, just as it was last week, and work questions 12 through 14. I'm going to end the lecture here. On Wednesday, we're going to talk about electron configuration and the electromagnetic spectrum. But if you have any questions about the practice problems here, numbers 12 through 14, I will have virtual office hours this afternoon from 1 to 4 p.m. You are more than welcome to come join me. I will send the Zoom link to you guys. All you have to do is click on the Zoom link and pop in. It doesn't have to be at 1. You can come at any time between that block, 1 to 4 p.m. All right. I hope you all have a great day, and I will see you in class Wednesday. Thank you.